Good afternoon.
Good afternoon, Doctor.
Good afternoon, Doctor.
So the slide is really I refer to slide 1. The material is 1 to 2. Is slide 2. Both left. It's 3. It's 3. We will start. You may download the book with it as well. Before to chapter 10, we could introduce this forward from Nigeria in the presentation. Just from here, we complete both. Goes from English 21.
Doctor, sorry to interrupt. Actually, your audio is not so clear actually.
Boleh dengar tak?
Yang this one okay. Tadi isi berapa? Memang,
Jelaskan saya kakak.
this one okay, Doctor.
How many of you working? 5, 3, good. Farid, Asrul, touch on which uses for which heat we cover economic, gas pollution, particularly water, this integration to book 1, 10, page 353, just for water management and minimization. In 2006, the author of this chapter introduced WMH, the management hierarchy, shown in figure 10.1. For 5 level, elimination to fresh water, source elimination, then top the hierarchy limit. Sometimes it is possible to eliminate water, then to reduce cycle. The elimination is not to eliminate the water, but to substitute it something else. For example, using water, we can replace it with air. That means the source, even though source elimination is the ultimate goal, possible we want to replace water with other type of media. Often it's not possible to eliminate water completely. So that's why we also have the parity. Attempt should be made to reduce the amount of water if the source of water usage. Such a measure is called source reduction. It's the second best option in the WMH. So we reduce the amount of water usage. So to reduce the amount of water usage, that's why we try this method, water each analysis into C. So when it is not possible to eliminate or reduce the fresh water at source, wastewater recycling should be completed. So level 3, 3 and level 4 in the hierarchy. Division two different modes, water recycling. First one, the third best option is to direct reuse sorting. And the fourth best option is regeneration reuse recycling. So the term reuse and recycling is the different meaning. So direct reuse may involve using spent processed water directly within the process system, subject to its quality being acceptable to operation. Meanwhile, the outsourcing here define the outsourcing involves use of available external water source, just the water. Through direct reuse or outsourcing, the country water of external water source is developed to which get the same lower quality. So meaning for direct reuse, we cannot reuse it again for the same process where the water source from, but we can use it for other type of process. In order to use the water from the same process again, that one we need to regenerate it, then recycle it for the same process. However, in most industrial application, regeneration level 4 may be necessary prior to recycling. Regeneration refers to partial partial treatment of wastewater or even external water source to match the quality of water required for the. There are two possible cases for regeneration. We have regeneration recycling. Both the reuse of treated water in the same equipment process to treatment for process one here. You want to reuse the water again from process one experience. Then you need to regeneration cycle. Regeneration reuse involve reuse of treated water in other equipment. So for regeneration reuse, meaning treated the water from process one, channel it to process two or other process, which can accept that contaminated water. How to know that water is enough? When the use is possible for that process. Have more discussion. Maybe not today. Today just introduce the so the last level, fresh water usage level 5 should only be considered when wastewater cannot be recycled or reused, or when wastewater need to be diluted to obtain a desired purity. So meaning we mix the contaminated water with fresh water to dilute it, then channel it to other process. Now, the wastewater has undergo end of pipe treatment before discharge to meet the meter guideline. The use of freshwater is the least desirable option, water minimization point of view. Ravi? Is to be avoided when possible. Through the WMH, the use of fresh water may not be eliminated. So, water footprint reduction there are another two tools. The management we have PCB life cycle testing. One would the footprint evaluate you share with you the papers. I share with Philip. It's paper by Dal here. Investigation of the carbon footprint reduction. Showing best available technique in the textile sector. Paper is from Turkey. So water footprint concept that expresses this is related to the pyramid just now of the management hierarchy. That express the measure of how much fresh water is used during the life cycle of a product. The water footprint consists of elements page 2 of the paper. So green water footprint represent the consumption of drinking water, soil. This is their definition. The blue water footprint, the fresh water, groundwater. The gray water footprint is the volume of water polluted with the surface of production process. Three type of blue and gray water footprint values using the chart chain sum method. The blue water footprint of the product is calculated with the total amount of water including the processes. Same amount. So WF products into WF process over process WF prop here. The process water footprint for water consumption liter per year. This is found in the recent paper. Although their application industry, but can be used for other type of industry as well. And while gray water footprint is using this water flow rate fine without the facility. So why they choose COD? Because we have many, right? We have pH, COD, yes, yes. They choose COD normally because COD represent the typical contaminant within the wastewater. Because wastewater normally consists of many type of contaminant. So one way to confirm, sorry, one way to look for the contaminant accounted for by measuring the COD. This one choose COD. So for W, this is where water footprint. WF is product A refer to pollutant dot per kilogram. From this. Okay. So that's different. Or so water footprint. One is from books. This from pinch analysis for regional water scarcity assessment. GR last year in 2023. The table is the image 603. Chapter 20. The time again. My slide is really year to last year, but each year I updated it. The footprint reduction, you can refer to paper row. The water footprint is one of the most commonly used filter. Yeah. Custom for water footprint. Other post-assessment tools such as life cycle costing, the pinch is this three is the water resource assessment. So the assessment type for water footprint in life cycle costing, I just touch it a bit. It's not the scope chapter. So assessment type for water footprint in life cycle costing is post assessment. Water pinch is being processed everything. For the assessing object, cycle costing is product, focusing on product. Water footprint, product process organization of region. For the, well, this is all the comparison. Go to the book. Complete of comparison. Final row should be for limitation. Water footprint. Limitation of water footprint. WF. Next step. Count only the input and output, not input for water used within the process. Life cycle costing, the limitation is have not been applied to resource assessment. Verify assessment. For water pinch analysis, challenging to consider multiple contaminant. Yeah. For multiple contaminant is very hard to do water pinch analysis. Natural water is not considered in there. So the concept is still two. The concept of life cycle costing developed by one actually in set here several decades ago is actually in 1981. The life cycle costing at the moment, I think the newest term, they combine it with life cycle analysis. Before that, it's a life cycle costing. So the LCC was designed to account for the total cost expended in support. The concept was mainly applied in industrial segment. So due to the comprehensiveness, it was challenging to be implemented specifically for you. Continuous data or life cycle of access item. Therefore, in practical implementation, most of the cases cover just part of the website. This is for, yeah, pinch analysis. So for like 14, so number 1. Yeah. No, yeah. Still in book 2, chapter 20. If you have the chapter downloaded, you can refer to page 605. So pinch analysis originate from systematic effort to improve recovery in industry through process integration. That pinch analysis, the first analysis, is actually to for heat recovery. What our Dr. Farid discussing. And water pinch, the most is one of the successful extension. And today is based on pinch analysis for heat recovery. So person responsible for water pinch, Professor Wang and so from the water pinch analysis developed by these two have several methods. Many method. So many methods. But the idea is the 5 key steps is similar. So compare with post-assessment tools such as WPA is water pinch analysis. It's a design and optimization tool in industrial water use. The one that's this point here is referred to the first paper published by Wang and Smith in 1994, but the method that they produced is published in 1995. I cannot find the 1994 paper by Wang and Smith. Yeah, show how to find it. The WPA is designed to integrate the water supplies and demand in industrial side, aiming to target freshwater input, wastewater generation minimization, and water network design. So WPA includes 2 types of approaches. The insight-based pinch analysis and mathematical programming based targeting method. So mathematical based targeting method is developed by Professor Pahavida and Prof. Zainuddin in 2013. The insight-based technique mainly include calculation-based technique, insight-based technique. Mainly include graphical targeting technique, this material recovery pinch diagram. Material recovery pinch diagram is developed by Professor Halwagi. Three. And algebraic targeting technique, material cascade analysis. So what's spread studies? It's also been conducted on topic of mathematical programming targeting. Okay. Now I'm going to page 606. A typical water pinch analysis solution is two step of setting the water type. Of setting the water target, followed by network design to achieve the target. So in the work of Mr. Wang, Smith, paper, the first paper, it's very long, 26 pages, because they cover single contaminant and multiple contaminant. Although today we cover first single contaminant first. So yeah, we can go for multiple contaminant as well. In the work of Wang and Smith, the target of using fresh water, maximizing water reuse and water regeneration are discussed, and both single and multiple contaminant are addressed in this 2019. So a composite curve used to represent the water using process approach can identify the bottleneck minimization in real processes. And the conceptual framework can help specify the optimal type of regenerator and regenerator specification. So their work serves as one of the earliest contribution of graphical method for water minimization study using WPS. So they actually developed the composite curve, LCC, limiting composite curve, to find the pinch point. The pinch point. Okay. So this is original paper, the minimization, GS. From the paper. So this info you can refer to page 981 or the first page of the paper. So if we exclude the possibility of making fundamental changes to the process, to reduce their inherent demand for water, there are three possibilities for reducing wastewater. So the first point here, you don't want to make any big changes. to the existing process. So what can we do to reduce the demand for water? Three possibilities: reduce, regeneration, reuse, and regeneration, recycling. So reuse, wastewater can be reused directly in other operation, providing the level of previous contaminant does not interfere with the process. Meaning after the water pass through the process will be a wastewater. In the wastewater, there are contaminant. So that contaminant does not interfere with the next process that you want to channel the wastewater. What's it mean? So reuse might require wastewater being blended with wastewater from other operation and or freshwater. Not that there may be recycling within an individual operation, but here we consider only the one is regeneration reuse. Wastewater can be regenerated by partial treatment, remove the contaminants, which would otherwise prevent its reuse and then reuse in other operations. So the term reuse here refers to, although it's already regenerated, but it's be channeled to different process, not the source of the what process that process where the wastewater coming from. Again, reuse after regeneration might require blending with wastewater from other operation and or freshwater. So let us emphasize that when water is reused after regeneration, in this case, it does not re-enter processes with. In order to use the wastewater again for the same process, you need to do a generation recycling. Wastewater can be regenerated to remove contaminants which have built up when the water recycled, and then the water recycled. In this case, water re-enter process is in which it has previously been used. So it is important to distinguish between these cases, the three cases here. In some cases, recycling between operation might be allowed. In other cases, it might not be allowed due to the build-up of contaminant not removed in the regeneration. So how to regenerate it? Method. Can filter it. Can use membrane to filter. Just ventilated carbon. Trap. Spatter. This paper referred to Wang and Smith before. So this paper will develop method to target and design for minimum wastewater for the above three cases. Although we will concentrate on example from petroleum refining, the methodology is capable of being applied to any type of process requiring water. just pub textile, etc. So meaning that this method is applicable to other type of process. So when you read this book, or sorry, paper, the example is based on petroleum. Still the paper, this is the chemical subchapter, page 982 page. Targeting minimum was better for single contaminant. For water pinch analysis step, we have 5 steps. Listed by Khalifah Rafidah. Khalifah, 5 steps. One is the analysis. What? Second one, data extraction. The third one is the setting the minimum utility target, which is targeting minimum waste water for a single contaminant. This is the third step by third step is actually the pinch analysis. We want to determine the pinch point, the minimum water usage for this case. For the water pinch analysis step, we will refer to one. And consider the water using pressure shown in figure 1A. This refer back to first paper, water minimization. Consider the water using pressure shown in figure 1A. This is the original picture. This paper is 1994. Process material is contacted with water in order to reduce the level of contaminant. So the process in, is out, water in, water out. So water here too. For example, could be a petroleum refinery desalter in which crude oil is mixed with water, extract salt from emulsify water in oil. The oil and water then allowed to settle with the assistance of an electrical field. Figure 1B shows a representation of this process in terms of concentration of contaminant versus mass of contaminant transfer. In the example of the desalter, so for figure 1A, let's say it's a desalter. So the contaminant would be salt, because the water will mix with the incoming crude oil plus salt or water. Contaminant is salt. Figure 1B shows one possible combination of inlet and outlet concentration of water to satisfy the mass requirement. Specifying the inlet and outlet concentration of water and the mass of contaminant transport also specify the water flow. So the information here, the M is flow rate kg per hour. Normally either in gram per liter or ppm. So this data is actually from the process or the mass balance. So clearly, different water flow rate and concentration can solve the same problem, figure 1C. In order to maximize the possibility of water reuse to this equation, we should specify water with the highest possible inlet concentration. So this one is the C process in this high contaminant, high flow rate, come out, contaminant is less. How come it reduced? Because we have incoming water. So this incoming water is from different process or from reuse or from regeneration reuse or regeneration recycling. Because based on the water management hierarchy, the last resort is fresh water. You don't want to use fresh water for all the process. Enough for other process. This one is page 2 of the paper. Second column. Then specifying the maximum possible outlet concentration minimize the water flow rate at the maximum in that concentration, figure 1D. This water profile shown in figure 1D will not necessarily be the profile we will use in the final result. So in this case, we come up with a limiting water profile, meaning this is the minimum water quality for that process. So meaning the incoming water profile must be less than this limiting water profile. This okay. It simply represents a limiting case. We will therefore designate this to be the limiting water profile. Any water supply line which is below the limiting water profile will meet the requirement of the process. Meaning, any water profile below the limiting water profile can be used to treat the incoming process in high level of this level of. So it doesn't necessarily the incoming water is coming from fresh water. If it coming from fresh water, the arrow will start from 0. So figure 1E shows two examples of figure 1E shows two examples of different water supply line which will satisfy the process requirement like this. So in this case, the one fresh water here below the profile. So the second line here is actually from a different process. That's why the concentration inlet is contaminated, but still below the threshold. So the threshold here is the limiting water profile. So how to determine the limiting water profile? That one we need to do the pinch analysis. The maximum inlet and outlet concentration for the limiting water profile will be fixed by a number of possible considerations. Maximum inlet and outlet concentration for the limiting water profile. So meaning this line. Okay, this is a number of possible consideration. First one is minimum mass transfer driving force, which might vary between different processes. Second one is minimum solidity. One that need to avoid precipitation of material for tradition, many possible considerations. So the limiting water profile. So in the same paper, the author provides example of limiting composite curve. How to determine the pinch point. Page 3. So the data for this example shown in table 1 is table. This is a very famous table. Just to do water material influence. It is this example almost in every book or paper as an example to give credit to these two professors. So we have 4 processes. The mass lot of contaminant is this is the flow rate. Is the concentration of it. Simply up the flow rate. Although it's shown here is in PE, ton. So 1 ton equal to 1.16 kilogram. Okay, let us emphasize that the data in table 1 represent limiting data. Maximum inlet and outlet concentration of contaminant. Also, in table 1, we assume that the mass transfer is a linear function of concentration. This is usually valid dilute system. Because we know already in wastewater there are many contaminants. However, if the behavior is significantly non-linear, the approach can still be used by representing the non-linear process as a series of linear segments. So, figure 2A What is the figure 2? The figure 2a shows the plot of the limiting water profile of each operation in table 1, shown in the graph in figure 2a. The water supply line for each operation, assuming that fresh water has been used in each operation. Because they use fresh water, that's why the limiting water profile started from 0. Same. No. 0. Which one supplies is still 0. That the progress has been minimized in each case by taking it all of constitution to a maximum. So this is for process 1. You see here from 0. This is y-axis is here. X-axis is the concentration in ppm or milligram per liter, similar. X-axis is the mass dot contaminant gram per hour. So for first process, mass lot is 2 kg per hour. C in is 0. C out is 100. So the limiting water profile is also 0 to 1. So but process 2 here, mass lot of 5. So the concentration in is actually 50. Out is 800. Limiting water profile. If you use fresh water, started from 0 to 100. So on. So figure 2b shows the design which would correspond with fresh water used throughout. Corresponding water flow rate would be 100 to 1.5 tons per hour. So how they get this number? Go to this table. This table row 100 is 0 times 50. How about the second process? 50 divided by 100 times the water flow. 50. So 50 minus, sorry, 100 minus 50 is 50. So this one is 50 divided by 800 times 40, then 40 minus the value of 50 over 800 times 40. So you get 37.5. So 50 over 800 times 40 is 2.5. So 40 minus 2.5 is 37.5. The freshwater usage 112.5 ton per hour. This is before water pinch. Oh, page 4, paper number 1. Is the pinch. We are to minimize the flow rate overall, must analyze using processes behave in an overall sense. For this, we can construct a limiting composite curve as shown in figure 3. This is a limiting composite curve. In figure 3a, this figure. Figure 3a, the inlet and outlet concentration of the processes, we find concentration. So this is process 1 from 0 to 1. This is process 1 from 0 to 100. The mass load is T2. We have 2 to 7 cumulative. We have from 50 to 100. Mass load updated for process 3. 1 to 7. Started from 50 up to 800. The last one is from 400 to 800 ppm. So this is the limiting water profile. So within each concentration level, the rate of mass transfer is constant with any of the processes significantly non-linear. They could have been represented by a series of linear segments, which would have created additional interval at the point of intersection segment. By combining operation within a concentration level, we obtain the limiting composite curve. This figure 3b is the limiting composite curve based on the water limiting water curve. So they combine process 1, 2, 3, 4 to become one continuous line. So figure 3c was shown. Figure 3c showed the water supply line match against the limiting composite. So from here, let's say we use fresh water to, as example 1, if using fresh water, started to 0 till you hit this point. So this is the pinch point for each element. The inlet concentration of the supply line has been assumed to be 0 by maximizing the outlet concentration of the supply line. Fresh water use, hence fresh water ignition. At the pinch, the driving force goes to minimum since the minimum mass driving force into the data. Alternatively, the restriction here figure 3c indicate that the minimum water flow rate, for example, 90 ton, I will compare with the 100 growth 0.5 ton per hour in figure 2b. This is a reduction of 20%. So how they come up with 90 ton per hour here? They don't show the calculation per this line. Calculate the ppm similar to percentage. For percentage, the number is divided by divided per 100. So ppm is per 1 million. That's why it's ppm. Part per million. So you have 9 kg per hour. Divide by 100. So to remove this ppm, you need to multiply by 1 million. Because it's part per million. Then you get the 9 times 10 to the power of 6 divided by kg per hour. Change this kg per hour to ton per hour. That's why they get 90. They get ton per hour. Nine times 100 divided by 1016 by 100. Yeah. Not yet. It's continuation in interpreting analysis. Go back to chapter 10, book 1. Actually, if you refer to the paper, after no, wastewater, target the setting the minimum utility target. Then you need to design for minimum wastewater for single contaminant. That one I will cover. Only from back to chapter 10, page 307, with the teaching system. Okay. WPA can be defined as a systematic technique of implementing water minimization strategy through integration of process for maximum water efficiency. In production term, the pinch refers to limits on productivity or bottlenecks. So Prof. Rafida, analysis, especially one. Term of mass recovery, pinch occurs at the smallest driving force that limits mass recovery. Of mass recovery. So water is assumed as a mass separating agent. State that function to remove to page 359. One. So the book one is the full title is Handbook of Process Integration. Handbook of Process. Many chapter inside the book. Chapter 10. Best revision. Okay. Water is assumed as a mass separating agent in stream that function to remove impurity from the rich stream of S6 product. So this includes the process such as absorption, so long as the new version of water pH analysis separate water source and demand section. Since then, WPA system have gone through various different WPA proposed for wastewater to be reused in a process that require less pure water instead of being discharged into wastewater treatment. The basic message of WPA is as follows: don't solve an end of pipe problem, end of pipe solution. Unless you have explored the quick process solution, your end of pipe solution could be existing. Which is true. This research. Because there's a issue here with high COD or in Lichet, sure which company. So Lichet, very high COD. But the company problem. Higher the prosecutor proposed filtration. This is case of in pipe problem. So what when they install here, of course it's will reduce the COD to very minimum. However, there's patented. Patented. Meaning once the high COD water pass through the membrane, you reduce the value. But this the high COD problem still there. Although you can discharge water, but this high COD water is still there. Meaning your solution is one let's explore the impossible solution. Your end of time solution would be the worst solution. Yeah, that one. Now they have bigger problem. The COD from the Lichet higher than before. What we do based on the pyramid size. We eliminate the water. Can do something else. Original for significance of water pitch analysis. Cheaper, many about this slide. You don't remember paper. Code significance of pitch analysis. It's generally easy to identify potential design improvement system and utility system that can yield good investment payback. However, it is difficult to be sure if the proposed scheme are the best for a given process, quite often technologies will be still. Can I do better? Even but until today, progress made in process design has largely been developed based on the learning curve. This figure, which analysis success factor with the design target. So Linhoff 1986 is referred to the first pinch analysis based on heat recovery by Linhoff and Flower in 1978. Linhoff then in 1986 come up with this. Cost saving, the time, past design fit. This is a design profit based on past performance. This one is based on chapter 10, handbook of process creation, book 1. Technologies would typically use a previous achievement the specific water consumption of similar plant elsewhere as a benchmark for improvement. Such benchmark can be referred to as an apparent target, since any improvement is only relative to the previous design achievement. So this statement referred to figure 10.3a. It not significantly improved actually over the past design. See, a true minimum target should be based on specific structure, operating condition, and thermodynamic of the plant undergoing retrofit instead of on the performance of a similar plant would elsewhere. This is where pinch analysis has a key advantage. It has been proven useful in representing the overall system water quality and quantity and in noting the true water target water efficiency. So with the notion of a true minimum design target made available through pinch analysis, authorities would be less likely to settle for a marginal improvement instead of this mere improvement. So they do the pinch analysis to get the step change. They settle for the marginal improvement and would strive to achieve the true minimum, hence the step change in improvement. So that one is figure 10.3 B. That's why we do pinch analysis. A promising project can be conveniently screened for the marginal one, while improvement can be quickly assessed simply by comparing the performance gap between existing design and the one meeting the true minimum target. Knowing the target and the maximum potential, moving ahead of design would be vital in steering technologies to the best achievement. Best pinch analysis. Terbuka. Pinch analysis for energy and carbon footprint reduction. And based on third book, analysis for energy and carbon footprint time Page 3. Water, hydrogen, and carbon olefin pinch analysis. This step in mass pinch analysis so 1 RV in Mandan 2013 identified 5 key steps to conduct a water pinch analysis. Can also be extended to gas pinch analysis. The step to conduct a mass pinch analysis is followed. Actually, it's from the book. They adopt it from book Handbook of Process Integration, chapter 10. It is what? The 5 steps of pinch analysis. The first one is of water network. First step is to analyze the existing or the best case water network through plant auditing. The second one is the data. I'm referring to the one because for this 3, they just phrase it. The second one, data extraction. The second step is to identify water source and water sink. The water source and water sink, that one term, that's 2 terms we need to understand. The water source is the contaminant. Water sink is the incoming, either you use reuse, or generated recycling, method reuse, or you use fresh water. That's why the term sink. So this is the source of the contaminant. So the sink is the source will coming to the sink or the clean water. The second step, okay, I think having condition for the use is something to extract the limiting product, limiting sugar. Non-limiting concentration in the water system situated at a concentration below their minimum limit and do not affect the water sink for that operation. Again, water source is the contaminated water or wastewater. Water sink is the water to clean the wastewater. Third step is to setting the minimum utility target. That one I already covered. That's on paper by one and Smith. First paper for water pinch analysis, 1994. The third step is to establish the minimum simple quantity of freshwater requirement for wastewater generation, or the minimum water target using a targeting method. So the method that I show you is the graphical method. You need to draw. There are another method, cascade method. You need to draw, you just calculate. But at the end is to find the minimum utility target. Or in other words, to determine the pinch point. Okay? Question. You can ask question. Yeah, correct, Jesse. Mass water source, mass source, mass the same. Source to dilute. Fourth step is water network design and retrofit. That one I haven't touched it. Tomorrow, see. Another 4 meeting. But at the end, only from my class, you learn about the water regeneration, recycling water regeneration you use, how to channel it to other process within the lab. Last is economic evaluation. The final step is to evaluate the economic of the water network. But economic evaluation, I think that one is check. It's covered by Dr. Asrul. Yeah, see. Process economy covered by Dr. Asrul. In July. It's actually part of the water pitch analysis. Okay. Flowchart mass pinch analysis. So this flowchart can only you need to refer to book number 3, page 355, chapter 9, figure 9.3. Actually, is based on the 5 step of the pinch analysis. So you start with network analysis, mass network analysis, water network analysis for our case. Extract the data, you target the minimum utility, and then you design it, profit it. Last one is the economic. So from here, then you create a loop. People have acceptable bacteria to design with safety and numerical constraint. So all this is okay. It become your final design. Otherwise, you need to return back to step. One. One. Step 1 here refer to book 1, handbook of process integration. Page 358. A good candidate for implementing water saving project include process unit, making high value product, process unit that are large water user, unit generating high toxicity waste, plant site with poor water availability or rising water costs, plant site undergoing expansion, process with plant site is problem, site with tightening with the regulation, done with capacity constraint in their wastewater treatment facility. So in implementing WPA for a plant, the overall network water network of the plant should first be obtained from PFD, process flow diagram, because from process flow diagram, we get the flow rate actually. For what case to do water pH analysis. And also you can get a heat as well. Heat from the PFD or the heat recovery pinch. Process and instrumentation diagram, PNID. Water mass balance is conducted for all the water stream. The mass balance data can be obtained from existing measure balance, computer monitoring, looping measurement, previous plant study, and laboratory report. Note that general water using operation can be classified into two main categories. This is still a step one. Oh. Okay. Still in step one. So water using operation can be classified into two main categories. We have a mass transfer base, MTB, and non-mass transfer base, NMTB. So mass transfer base operation, refer to page 359. And MTB using operation is characterized by the preferential transfer of species from a rich stream to water which is being utilized as a lean stream, or MSA. MSA is referred to mass separating agent. So if you're using water to dilute the contaminant, so your water is MSA, or mass separating agent. This can be clearly illustrated by a mass exchanger block diagram in figure 10.4. 10.4. So the incoming lean stream is water. This one is, this is the MSA. This is the process type. Two major examples of MTB, mass transfer based operation, MTB, the using operation are cleaning and absorption, AB. Cleaning involves the preferential transfer of species contaminated from a rich stream. In this case, the equipment watch to a lean stream or MSA. In this case, water. So figure 10. Figure 10.5a shows the water used for cleaning process as a sink and the wastewater directed as a source. You see here the term. For an absorption process, water is the MSA used to remove contaminants such as H2S and SO2. As the name said, mass transfer based operation mass transfer. Note that the input and output flow rate of the mass transfer process assumed to be the same, since this type of operation is also known as fixed flow rate problem. Okay, next is non-mass transfer based operation. Till step 1. An NMTB water using operation cover function water other than MSA, mass separating agent. For example of such operation is water being utilized as heating or cooling medium where there is no mass transfer involved. For such operations, sometimes only water sink or water source exists. Shown in figure 10.6, water goes into the system but is lost as it evaporates. So for this, which one? 10.6 or 10.6 here. 10.6. So water goes to the cooling tower. There's no water coming out because it turned to vapor. Similar to boiler. So water goes to the system but is lost as it evaporates in figure 10.6a. For figure 10.6b, water is generated from the condensation of steam from the boiler. Another example in cases where water is being fed in as a raw material. For example, at 10.7 there. Water as a heating or cooling medium or as a raw material fed into reactor is not intended to preferentially transfer species within stream, hence it's clearly present non-mass transfer operation. Note that water flow rate is more important than the amount of contaminant accumulated for an MTB, non-mass transfer based operation. Water using operation for this reason, an MTB process can have different inlet and outlet flow rate. The NMTB version is also known as a fixed contaminant load problem. Better. So for MTB, mass transfer base, the name also known as a fixed flow rate problem. For NMTB, non-mass transfer base operation, also known as fixed contaminant load. Note that water source and sink stream having the potential to be reused need to be identified. The key contaminants such as COD, BOD, TSS, chemical oxygen demand, COD, biological oxygen demand, BOD, total suspended solid, TSS, total organic content, TOC, and total dissolved solid, TDS, that prevent direct use in the water system with its limits into a process within the wastewater effluent is to be identified. The three most important key contaminants are normally chosen. So from all the key contaminants here, we choose 3 to analyze the water. For this one, this slide, contain binary hydrogen distribution system. Typical process involve hydrogen consuming processes such as hydrotreatment and hydrolysis. Hydrogen producing processes, reformers, can purify processes. membrane separation, pressure swing resorption, and cryogenics. So these processes are an MTP operation before hydrogen system are fixed flow rate problem. So in general, the outer stream of the process unit are the source stream, whereas the inlet stream are the demand or sink. Okay, this is similar to the heat action. The output product tend to be heat soft, heat sink, both. Step 2, data extraction. So after analyzing the water network, the MTB and MTB, the water processes are grouped into plant section. Processes chosen are preferably close geographically in the plant. Location is close. Also chemically related. The process needs that chemical. The main contaminant that prevent direct reuse in the water system are chosen. The system can be modeled either as a single contaminant or a multiple contaminant approach based on the water quality plant process. However, the problem of multiple contaminant involve complex modeling procedure and relies on mathematical modeling and optimization technique. So an alternative is the use of aggregated contaminants such as solid, oxygen demand, TDS, that allow multiple quality factors to be modeled in single contaminant approach. Although it's a multiple contaminant, we can choose key contaminant such as TDS, solid, COD, to model the multiple contaminant wastewater as a single contaminant approach. The modeling of aggregated contaminant as a single contaminant is known as a pseudo single contaminant system. The proposed network then need to be reassessed by checking that all other contaminant classification procedures are still within allowable limits. Before implementation. So the entire water source and sink flow rate quality requirement for each water using process are extracted. The water source data are obtained by identifying the maximum concentration. Process. The water sinks data are also usually obtained from historical variation, emergency water substitution, estimate from engineers, vendor, and operator, and description. Data extraction. You still remember table 1? Paper water minimization. In table 1, this data extracted it from the talent from step 1 analysis of water network. And they came out with this 1, 2, 3, 4. Central flow rate. Step 3 is setting the minimum utility. So first, setting the minimum utility target. We have many methods. One I show you, limiting compositor. So in handbook of process integration, chapter 10 here, refer to page 261. So for this book, list out 6 methods. My slide will be limiting compositor, water surplus diagram, sourcing compositor, the cascade analysis, algebraic targeting approach. Last one is source composite. Yeah, this is based on view. First one of compositor. That method is in 2006 with LCC. LCC is at page 352. So based on this handbook, it referred to the actual paper, 2024. The LCC was introduced by Wang and Smith. Only applicable for NPV, mass transfer, gas operation, or fixed flow rate problem. The LCC is a plot of contaminant concentration versus contaminant mass load. Each water using process is assumed to have fixed flow rate. There is a transfer of mass load from process stream 1 to process stream 2 from figure 10.4. In the LCC, each process stream has an inlet contaminant, outlet contaminant concentration. This is similar graph plotted on the LCC. LCC is a limiting compositor. The streams are then composited according to the concentration interval. Limiting fresh water supply line is drawn starting from zero because it's a fresh water. And mass load with a slope to just touches the compositor at one point here. The water supply line has to be located below the compositor with the minimum flow rate target for the system. For supply line of touches point system the each point. Water cascade analysis. This is page 363 in book 1. The WCA water cascade analysis is a numerical targeting method with the aim of establishing the minimum water target, the overall freshwater requirement and wastewater generation for a process after looking at the possibility of using available water source within process to meet its water sink. So to achieve this objective, the net water flow rate, water surplus, and deficit at different water quality level within the process of the study have to be established. So, Manan et al. 2004 referred to Professor Zainuddin Abdul Manan. He introduced water cascade table for this technique. So for water cascade, no need to draw, just calculate. A conceptual illustration of how water cascading can minimize fresh water need and wastewater generation is represented by figure 10.9. This figure. In figure 10.9a, first one, 100 kilogram per second wastewater is produced by a water source at purity level of 0.9999 100 ppm, and 50 kilogram water is needed by a water sink at the purity level of 0.9998 to 100 ppm. So without considering water reuse, so 100 kilo of wastewater would be generated while 50 kilo of freshwater would be returned. However, so this is separate system. So this system require 50 kg per second of freshwater to offset the 200 ppm. Meanwhile, this process produce 100 kg per second of wastewater. So how much water wasted? 150 kg. Okay. Without considering water reuse, 100 kg of water will be generated while 50 kg of water will be required. However, as shown in figure 10.9b, this figure, by making use of the 100 kg of water source at the purity level of 100 ppm, to satisfy the water sink of 50 kg per second at purity level of 200 ppm, it is possible to avoid sending part of the water source directly to effluent. So 100 kg here is actually water source, wastewater. And instead of send it to wastewater treatment, they channel it to this process. So doing so not only reduce why we can channel it here because the concentration here is below the threshold. Doing so not only reduce wastewater generation but also freshwater consumption in both cases by 50 kg per second. So a general structure of WCT water cascading table. Water cascade table is shown in table 10.2. First step in setting up the WCT, the cascade table, is to list all the contaminant concentration C of the water using process, remove duplicates if any, paper by Manan 2004. Because this table is from that paper actually. Okay. Remove duplicates if any and set up the contaminant concentration table in ascending order. So from 0 to the highest. As illustrated in the first column of table 10. So later we will have a case study how they apply water cascade table analysis for 10 gas farm somewhere in Daido. Next, the purity P of each contaminant concentration, column 2, is calculated as the concentration of pure water is 1 million ppm. Water purity of contaminated stream is defined as purity P equal to 1 million. P is equal to 1 million minus C over 1 million. So C here equal to the contaminant concentration ppm. That is how you get this column. Next is in the third step, each step refers to each column. In the third step, the purity different delta P. So delta P here it's not referred to pressure, it's referred to purity. It's calculated using equation delta P equal to Pn minus Pn plus 1. So in this table, 10.999 minus 0.99986. So you get 0.0001. And so on. So 10.99 here refer to 10.99 refer to C10, 0.9986 refer to 40. This one refer to here. P is in between 0 to concentration. Could be. The flow rate of the all water sinks, FSK, and source, FSR, are summed at each purity level in column A, F, FSK, SR, respectively, for simplicity. All summation will be presented by summation in the following text. Note that water sink are written as negative value while the source are positive. Source is the wastewater, the sink is fin. The water sink So I find you the paper by Manan. How many steps? For water cascade analysis, you have 9 steps. Refer to the each column of the water cascade table. The fifth step refer to the fifth column. Okay, the fifth column is FSK plus FSR. SK refer to sink, SR is source. For different purity level, positive value in this column, that's the plus of water present at the respective purity level. A negative value signify net deficit of water. Any water sources at higher purity can be used as a source for water sink with lower purity. So from refer to this table here. So minus 1.2 sourcing is negative, source is negative 1.2 plus 0.8. 0.8 is actually minus 0.4. Nah, itu lah. Next is column 6, the summation sigma F, summation F. The column cumulative flow rate. Water in the sixth column is cascaded. The first row of this column represents the estimated flow rate of fresh water required for the water using processes. The estimated fresh water flow rate value will be added to the value in second row in column FSK plus FSR to get the cumulative interflow rate. So this cascade process will continue until the last value in the column. The total cumulative water flow rate value in the final column represent the total waste water generated in the process FWW. is table in a book of process division, book 1. Yeah. So this type is based on the 12 paper by Manan et al. The cascade and systemic. First step. The first step in the BCA is to set up the level water balance table to determine the net water source to be moved. Okay. The first column of table 2 then the contaminant concentration setting order. It's one. Then the so 1 million here. As the concentration of pure water is 1 million ppm. The water quality of the contaminant stream is defined as so 1 million here is the pure water. I will say this is a contaminant. Yeah, water. This concentration level is expressed in terms of the water purity, second column. With the concentration of your water set at 1 million, the fraction of the water in contaminated stream of the water purity can be expressed as P equal to 1 million minus C over 1 million. Similar, it's similar to Upu handbook of process integration chapter 10. So second column, this column, 1 is 1 plus 1 million minus 0 over 1 million. So 1. And you get this one, you get 0.9999 and 999 Tetapi the water pretty different. P in column 3 ada sengaja ambil. Of table 2 is calculated as the difference between purity level and table K and K plus 1 as follows. So tetapi purity difference here refer to in between the level, between the concentration. So 1 minus 0.99990 is equal to 0.0000. But plus is 99966 minus 0. So we get this number. This is the water cascade. This is we still in step 3. So step 3 we have 6 methods. First one is a composite curve. One I will mention to you. Now is the water cascade thesis developed by Prof. Zainuddin of UKM. So column 4 and 5 contain the total flow rate, water demand, and the source corresponding to the level. So the flow rate of water demand is fixed as negative, and the source is positive. How you get this value? From the best value. Step 1 and step 2. Check the data file. For the water demand, If 1.2, 1. So 0.8. So the water source doesn't necessarily fresh water. It might be from reuse generated for those. This flow rate sum up at each purity level to give the net interval water flow rate FD plus FS, column 6, FD plus FS minus plus 0.8. Or if 5.8 this one is 0, then we have 5 up and down. So plus efficient net water source minus is net water demand. The water cascade analysis technique, once you get this, you can plot the water cascade now. So each purity level 5 and FW. So fresh water at the moment is 0. G fit for fresh water. G for water. First one is negative 0.4. We get the negative from volume number 6. Second purity level, negative 5.8, and so on. Step P is the purity difference. Then motif water source of demand C, so minus 0.4, kosong minus 0.4, negative 0.4, negative 0.4, minus negative 5.x, negative 6.2, negative 6.2, plus 5, negative 1.2, negative 1.2, plus 5.9, 4.7, 4.7 plus 1.4, 6.1. So wastewater produced is 6.1 kilogram per second. That one is for the figure 10A, water cascade again with an assumed freshwater flow rate of 0.3 per second. So B here, what pure water cascade is used to check the feasibility of the water cascade. So 0.4 times delta P, you get 0.0004 kilogram per second. Okay. Gas efficiency, that is the interval. The next step in the 1NCA is the freshwater and wastewater get for the process. And so it is important to consider both the water flow rate values and execution reinforce water purity so that the true minimum water get can be obtained. The water flow rate balance involves using the water cascade diagram figure 10 to obtain the cumulative net water source demand for a process FC. What will do it? So the water cascade diagram in figure 10A, the explanation. Freshwater flow rate is 0 assume. The net water demand of 0.4 at the first purity level is cascaded to the second purity level to meet another water demand. Second, giving a cumulative net of negative 6.2. This cumulative demand meets only net water source down the next 3 purity level to yield a cumulative water source or wastewater flow rate of 6.1 kilogram per second, the lowest purity level of the water cascade diagram. In addition to considering the water flow rate balance, the true minimum target lastly by so taking into account the pure water surplus or deficit, which is a product of the collective net water source demand FC, and the pretty different delta P across two pretty level figure 10 in B. Tidak ni dapat ni. A pure water surplus plus means water is available with purity higher than what is required in this region. Pure water deficit or negative means that water of higher purity than that available is required. Negative. Tiga level. Cascading the pure water surplus or the down the purity level cascade that represent the cumulative amount of pure water surplus or deficit. Notice that the pure water cascade in figure 10B, cumulative pure water deficit observed from second to fourth purity level into P and P4. The deficit on negative deficit on the pure water cascade indicate that the pure water cascade is invisible. Deficit means there is insufficient fresh water in the network and are the result of assuming zero freshwater flow rate FFW during water cascading. Because the first time we do was to escape the freshwater feed flow rate was set to 0. Later we determine the pinch response. Additional freshwater should be supplied to remove all pure water deficit and yield a feasible pure water cascade. So meaning pure this here must be in positive. So fresh or pure water is to be supplied at the highest purity level. To minimize fresh water, it is necessary to determine the minimum flow rate of fresh water or interval fresh water demand that will specify the total requirement of level. The interval freshwater demand will restore a feasible pure water cascade throughout the entire water level. All of this negative will be turned to positive. Figure 10C shows the interval freshwater demand WK for each purity level K is obtained by dividing the cumulative pure water surplus by the purity difference between the freshwater surplus FW and level this is good. Untuk dapatkan yang ujung, use this expression. Referring to figure 10C, a negative value of for FWK means there is insufficient fresh water, whereas positive means there is excess fresh water at the purity level K. It's started excess at purity level 5. To ensure that there is a sufficient fresh water at all points in the network, a fresh water flow rate is of exactly the same magnitude of the absolute value of the largest negative FWK, this one, negative 1.68 kilogram per second, should be supplied at the highest purity level of feasible water cascade. Figure 12. Sorry, 2.057 is that. So 2.057, the term here, the highest purity level of feasible water cascade means to supply fresh water. Do again the water cascade, but now the fresh water is included based on the highest cumulative pure water surplus. So this cumulative pure water surplus, because you use that number as reference for FW, fresh water, it automatically become the pinch of this process. So FW of FW value of 2.057 kg per second found at the third purity level P3 in figure 10C has the largest negative value. This quantity of the highest level, the stable water cascade. Note that feasible water cascade is the one that results positive or at least zero cumulative pure water surplus to the pure water cascade. To recalculate, but this one still refer to the water cascade table. The only difference is cumulative water source or demand AC 2.057 minus 0.4 get 1.657 minus 5.8 get 0.157. The feasible water cascade yield the true minimum fresh water flow rate of target of 2.057 and at the third purity level P3 equal to of figure both there if zero if pure water surplus is the pinch AN problem. AN here referred to acetonitril. This is based on acetonitril process. The pinch is the most constrained part of the network, representing maximum recovery. Through the WCA, we have obtained the utility target head of design and are able to verify whether the proposed solution design is achieved. Water cascade and pure water surplus cascade diagram form the water cascade table in table 3. This table 3. So this is the final table. Oh, it's the pinch. So the purpose of you do a lot of explanation is to determine the pinch. Any method you can use limiting Corsica. The outcome will be the same. The pinch point, although the accuracy wise, that one is depend. If you use water cascade analysis, at the end you can get the minimum utility target. Once you get the minimum utility target, then you can go for step 4 to design the network. profit. So WCT, water cascade table, the WCA, water cascade analysis. Technique offer two other key advantage over the water surplus diagram, realizing the minimum water target. Apart from its power to eliminate tedious alternative step, water surplus diagram. The water surplus diagram is different method to quickly yield the exact utility target and pinch location. The first key advantage is that WCT clearly display both the minimum fresh water and wastewater flow rate target in the cumulative net water source demand column. This is the advantage of using water cascade analysis. Second key advantage of using WCT is that it enables a designer to clearly identify the pinch causing stream and exact water location for the region above a minimum pinch. Referring to table 3, cumulative network pure water surplus of 0.99986 represent the pinch point. Note that the pinch closing stream, which is level is the water source. With the source. With a total flow rate of 5 kilograms per connecting to level 1, this strip is a single water source that is of gas condensate. Cepat bola. Third method is sourcing composite curve. The sourcing composite curve is used to target the minimum usage of fresh resources. Second is network, but this step for accepting the term of the water system. Rank the string in ascending order of the global contaminant concentration. So similar, mass load here is C. No, mass load here is okay. Not similar to composite curve, to limiting composite curve. This one's y-axis is concentration, C, ppm, while x-axis is the mass load. For this sink source composite curve, the y-axis is equally the M, mass load kg per hour, mass load of the contaminant. While a flow rate is referred to the water. Rank the sink and ascending order of maximum allowable contaminant concentration. When you rank, you actually put the table. Source ascending order of maximum allowable contaminant concentration. Got the maximum mass load of the flow rate is because of superimposing the sink level. I get one process, we have 1, 2, 3 source. Tiga sama lah. 3 proses, 3 proses. If one shift the source of the stream until it touches the sink or stream. So this source line, shift it till it touches the string line here at one point. Example here. So this point when it touches or tangent to string curve, which point here. You know. The difference here, once you break the source curve, see the difference here, this difference is the freshwater flow rate, and while here is the wastewater. So this method is proposed by 2003. So after targeting, the next step is consider process modification. Process modification are changes made to the input water using operation to modify either the flow rate or distribution of the system. The appropriate step to modify a process depend on the location of the process. See, relative to pinch point of the system, the process will be above the pinch, below the pinch, at the pinch point. This is for thin source compositor. So for above the pinch, the initial changes can be achieved by either increasing the flow rate or the source by decreasing the water requirement C plus. Above the pinch, thus below the pinch, the plus water below the pinch. Any flow rate changes not will affect the target. Exception to this rule of thumb is the case the source is the region above the peak. This is the case of regeneration. This is above the pitch. Suppose the pitch happen here. This is below the pitch and at the pitch. At the pitch, increasing the flow rate of source of the pitch, actually not is the target. So that only two possible scope possible vision to reduce the target in better assumption and is low. This our third regeneration and equipment modification. Propose a targeting technique in the elimination, segregation, recycle, intersection, and research manipulated. So Halale to reduce a guideline for reduction and regulation investment, effective analysis. Following further explanation. So we continue step 4. After network design and traffic. book by book one and book of process integration using sync source sourcing application for using the sourcing. Invest all. For attendance, take attendance first. Thank you. And Mr. Farid told me need to submit. You need to submit progress report. One for your group by today. Reminder from Dr. Farid. Hey. Ni. Okay. So any question you can ask. The chat box.